Let's take a look at this rates of reactions question. The question reads, the reaction between aluminium and excess sulfuric acid is used to investigate factors affecting the rates of reactions. Investigation 1, the effect of a catalyst on the rate of a reaction is determined. Aluminium powder of mass 5 grams reacts with excess 0.1 moles per dm cubed H2SO4 at 60 degrees Celsius. Consider the following energy diagrams not drawn to scale. For this investigation, X and Y in diagram B represent the activation energies. Okay, so they tell us that X and Y are the activation energies. Let's just make a note of that because it's going to be important. 5.1.1 is the reaction between aluminium and dilute H2SO4 endothermic or exothermic. So from the shape of this graph on the left, diagram A, we can tell that this is an exothermic graph. You can easily remember it. An exothermic graph will be a graph that starts here and ends lower. So that's an exothermic. An endothermic graph will start low and end high. That's endo. So in this case, it is an exothermic graph. Give a reason for the answer. And what reason can we give here? We can say that the energy of the products is lower than the energy of the reactants. Right? We can read that from the graph. We can see here that the products is 86.5, reactants is 208.2. 5.1.2, what does the shaded area to the right of line P represent? Now, that is a Maxwell Boltzmann curve, and a Maxwell Boltzmann curve will have a shaded region. That shaded region represents the number of particles, or the particles that have energy greater than the activation energy. So it's a small number of particles. 5.1.3, determine the numerical value represented by letter X. Okay, so important, that's why we highlighted this at the start. X and Y represent activation energies. So they want to know what is X. Now, remember, the use of a catalyst has a singular purpose: to speed up the reaction by decreasing the activation energy. So Y represents the activation energy with a catalyst, and X would represent the activation energy without a catalyst. Now, where do we get this from? We can get it from diagram A. Now, in diagram A, we have two curves. The curve that I'm going to highlight here in yellow, this one right here, that's a lower activation energy. So this curve represents the activation energy with a catalyst. The curve that's above it in green, that's representing the activation energy without a catalyst. So they want the activation energy without a catalyst. So to calculate the activation energy, you take this maximum energy value here and you subtract it from the energy of the reactants. So 5.1.3 simply going to be 240.8 minus 208.2, and that gives 32.6 kilojoules. Taking a look at the next part of the question, the investigation is now repeated at 30 degrees Celsius. So it was 60, now it's 30, using the same reactants and catalyst. How will this affect each of the following when compared to investigation 1? So the size of the shaded area. So they want to know how is it going to affect that. So let's take a look at a Maxwell Boltzmann curve like this. Now, if that's my activation energy and this is the shaded region, if we decrease the temperature, it means that more particles are going to have less kinetic energy. So the peak this peak right here is actually going to shift to the left, and it's going to move slightly up. And so a decreased temperature graph will look like this. And so what you'll find is that the area of the shaded region gets smaller. So the size of the shaded region is going to decrease. The value of Y, what is Y? Y is the activation energy. Changing the temperature is not going to affect the activation energy, so it's the same. And the total volume of hydrogen gas produced, that's also going to remain the same because we are not increasing any quantities. Right, question 5.3, investigation 3. In this investigation, 5 grams of the impure aluminium reacts with excess diluted H2SO4 at 60 degrees, so back to normal temperature, in 3 runs. The table below summarizes the conditions and the results obtained. Okay, so we have run 1, run 2, run 3. Now in run 1, the concentration was 0,1, run 2 it was 0,2, run 3 it was 0,4. So write down the independent variable. So in this investigation, the independent variable is the thing that they're changing. So they are changing the concentration of H2SO4. That's what they're changing. Each time they repeat the experiment, they're changing the concentration. And so that's our independent variable. 5.3.2, use collision theory to explain how the average rate of the reaction is affected in this investigation. Okay, so if we increase the concentration, as they are doing now, so 5.3.2, if you increase the concentration, we have more particles per unit volume. If you have more particles in a container, then there's going to be more effective collisions per unit time, and therefore you're going to have an increased rate. 5.3.3, this is a 6-mark question. The time for the reaction to reach completion in run 3 is 2.6 minutes. Calculate the percentage purity of the aluminium. Take the molar gas volume at 60 degrees Celsius to be 27,000 cm cubed per mole. Okay, so what we should start with first is our rate equation. So in this case, the rate is going to equal, let's look at the units. They are using centimeters cubed per second. So rate is going to be centimeters cubed divided by seconds. Right? We know the rate for run 3. They've given that to us. It's 40. So 40 is equal to centimeters cubed, or volume. Centimeters cubed is just volume, divided by seconds. Well, they tell us that it's 2.6 minutes. So we need to convert that to seconds. So 2.6 times 60. Now we can calculate the volume or the centimeters cubed. We'll say that the volume is equal to 40 times 2.6 times 60, and that is equal to 40 times 2.6 times 60, 6,240 cm cubed. Now what is this? This is the amount of H2 produced, of H2, right? This is the volume of H2. And now we know the molar volume, we can calculate number of moles. So the number of moles of H2 is going to equal the volume divided by the molar volume. So number of moles of H2 is going to equal 6,240 divided by the molar volume, which is 27,000, and that's equal to 0.23. So we have 0.23 moles of H2. But remember, we want aluminium. So we now need to do a mole ratio between H2 and aluminium. So if you look at our reaction, aluminium and H2. So the ratio between aluminium and H2 is 2 to 3. Where am I getting those numbers from? the coefficients. Okay? But we don't have 3 moles of H2. We only have 0,23 moles. And we want the number of moles of aluminium, so let's call that X. Now we can cross multiply. So 3X is equal to 0,23 times 2. That means X is equal to 0,23 times 2 divided by 3. So X is equal to 0,15 moles of aluminium. Now that we have the number of moles of aluminium, we can calculate the mass of aluminium. So remember, number of moles is equal to mass divided by molar mass. 0,15 is equal to the mass divided by 27. 27 is the molar mass from the periodic table. Now you cross multiply. That gives us a mass of aluminium, 4,16 grams of aluminium. Now remember, they told us at the beginning that they used 5 grams of aluminium, but only 4.1 grams was pure. So to calculate the percentage purity, that's going to equal the mass that's pure, the 4,16, divided by the mass, the total mass, times 100. And that's 83.2%. Okay, that's the video. Thanks so much for watching, and I'll see you in the next one. Bye-bye.